lecture today. And while we're waiting for the lights to come on and the action to begin, let's, whoa. All right. The volleyball team will be playing this weekend, starting tomorrow, at the NJCAA District L/M tournament. Now, I don't know what all those initials stand for. My guess is National Junior College Athletic Association. That's just a guess for NJCAA District L/M tournament. I don't know what that means. Maybe we're District L&M. I don't know. Or ladies and men. I don't know. But they're playing this weekend up in Boaz, Alabama, up in some of your necks of the woods. And that's at Snead State Community College, I assume. And that will be Friday, Saturday, and Sunday. Tomorrow, Saturday, and Sunday. Okay. So if you're up in the Boaz area, stop by and cheer our team on to victory. We have a very, very good team. They hopefully will do quite well. And then I think I've announced to you before about the 1-week summer opportunity for college students interested in biopharma manufacturing careers. Okay? 1-week summer opportunity. They will pay you $1,000 for that week and pay your travel expenses as well. That sounds like a pretty good idea. So if you're interested in biopharma manufacturing careers, that's biologic and pharmacology, in other words, making drugs, okay, legally, okay. The deadline for this is sometime in January. That's all the information I've got except for this website. If anyone's interested, come get this piece of paper, get the information from it, and good luck with that because it sounds like a great deal. All right. Any questions on anything we've covered so far? All right. Just a quick reminder. 2 hours of class started a while back, but okay. Then we'll stop there at 5:15. So let me know when 5:15 approaches. Stop at 5:15, and then we'll have 2 hours of lab. I doubt if it'll take you 2 hours to do the lab. I've got most of the equipment up here. I've got the lab sheets, all that kind of stuff. We'll do the lab, okay? And then we'll come back to the classroom here and have the test, okay? The last 30 minutes will be the test. This is the test from Chapter 2, okay? Now remember, you can have a formula and equation sheet, so if you don't have that formula and equation sheet, you've got some time to put it together, and let's try to get that done this afternoon. Now, I may have told some of you, because 2 of you may have asked, one of them's not here, that we might be able to, do some makeup stuff after things today, and we still can. However, if I could get away a little earlier than normal, I wouldn't mind it because my wife's out of town and she left the dog in, of course, but the dog has one of the biggest bladders I've ever seen. I don't think we have a problem, but the sooner I can get home, the more relaxed I'll be about that. Some days when Karen doesn't go in too early, she won't even think about it and then realize like 10 o'clock that the dog still hasn't gone outside. She's been 12 hours. So Karen left about 9 this morning, so I'm sure she put her out then. But I don't want to press it too hard. Okay, so any question about what the setup today will be? Okay. Today's a pretty fun lab. I think you'll enjoy it. I don't think it'll take you that long to do, but you'll have all the time you need if you need it. So no questions. All right. Now where we left off last time, let's get current slide up here. We had talked about this. Potential energy is the energy associated with position, whether it's position vertically, that's gravitational potential energy, position on stretching or compressing a spring, That's spring potential energy. There are other types of potential energy that basically are, they even mention electric charges, where an electric charge is relative to other charges. That's electrical potential energy. Okay? And I think we got all the rest of this. This next, the last bullet is really on the next slide. Okay? But while we're on this slide, here is our good old 4-story building. Okay? And someone totally dislikes their physical science book because they've tossed it out of the 4th floor window. Okay? Now, or they didn't. They may have just dropped it onto the floor. If they did, then their reference level is here. You measure the height based on some reference height. If as far as that book can fall is just to the floor of that 4th story, then that's the H that you're dealing with. But if they did hold it out of the window and drop it on a something, then this would be the height. But if you had chosen this height but dropped it this far, then you wind up with negative potential energy, which is okay. Okay? Just a little weird, but it's okay. Because if your reference position here, if that's your 0, mgh, if that's 0, the potential energy is 0. Anything below that, the H is now negative, so this would be negative mgh, which is strange. So I always suggest choose your reference height as low as the object can go in that given situation. The next lab, the one we do on Tuesday, will be, we'll choose one of the first things we'll measure is where our reference height is. Okay? And we'll be doing that next time. Any questions on this illustration of potential energy? Okay. And the good formula to note, though they didn't write it on the slide, they did write it, on the verbiage part, potential energy, especially gravitational potential energy, mgh. If that was spring potential energy, it's something different. But gravitational potential energy, mgh, you see G's in there, acceleration due to gravity, height's in there, that's in the direction that gravity is pulling. Okay. Now, before we move to kinetic energy, which is where that last bullet probably belonged, let's do the examples on potential energy. Example 3.5 at the bottom of the first column of 69, top of the second column. Okay, I'm going to back up one slide so I have more room to write. What is the potential energy? Okay, and this will be gravitational potential energy. So I'm going to call it GPE. Okay? Number one, you'll be seeing that on the labs that I make up because I like to distinguish between any other potential energy and gravitational. So this is the unknown. What is the potential energy? That's what we don't know. Of a 214 kilogram book. 214, that's not right, 2.14, okay? 2.14 kilogram book. What's that a measure of? Mass. That's a measure of mass, okay? That is on a bookshelf 1 meter above the floor. So what's that 1.0 meter? That's your height, okay? Now, we're going to assume the floor is our 0 reference level. So that's why we're measuring the height from that level, okay? So what would be the GPE? Anyone remember the formula for GPE? It was just up there on the screen. MGH. Okay, so let's start plugging and chugging. GPE, that's the thing we're looking for, is equal to M. What's your M? 2.14 kilograms. What's your G? Say again? We don't. Oh, that's 9.8. We do know that. Meters per second squared is an acceleration. So meters per second squared is a great units for it. And we're in the SI units because we're dealing with kilograms and meters. So that's why we use 9.8. If we were in U.S. customary, what would we use? 32 feet per second squared. Okay? The SI, 9.8 meters per second squared. And then finally, what's your H? See H? 1.0 meters. Okay? Now, just a minute, we'll do the multiplication. Let's look at the units first. Kilogram, meter squared per second squared. What's that going to be? Kilogram, meter squared per second squared. Ladies like them? Joules, of course. Okay. All right. Men like them too, I think. Okay. Now, 2.14 times 9.8. I'm not really hankering to do that one in my head, so someone do that. Say again?
20.97.
3.97?
20.97.
Ooh. Oh, 20. Okay, I can't hear well. That makes sense. 20.97, is that what you said? Mm-hmm. Okay, now what we have to do is now consider significant digits. How many we got here? With the mass? 2, 3. How about here? 2. How about here? How many can we afford here? 2, the least that you have. So count 1, 2, look to the right, there's a 9. That's going to bump the 0 up to a 1. That would be 21 joules. Okay? And that's what they got in the book. You could also call this Newton meters, because a kilogram meter per second squared is a Newton, times a meter is a Newton meter. Goodness, there's sun out there. That's surprising. Okay. And a Newton meter is a joule. Okay. Got it? Any questions on that? Okay. Let's go to 3.6. How much work, this time we're looking for work. Interesting. Can a 5 kilogram mass do 5.00 kilogram? What's that a measure of? Oh, they told us. Mass. Okay. Do if it is 5.00 meters above the ground. What would that be? 5.00 meters. Notice I said above the ground, so we're going to assume the ground's our 0 reference level. What would that be? Second? Height. Okay? Very good. Now, a little bit different type of a problem here. How do we define work? Same type principle. Oh, that was a long time ago, wasn't it? What did we say work was? Way back at the beginning of the chapter. Force times the displacement. Okay? Force times the distance. Now this distance is our height here. What's our force? Say again? You may have said it right.
Mass times acceleration.
Mass times acceleration, because mass is a mass, it's not a force, but mass times acceleration, that is a force. So our formula is mg, there's the force, times the height. Same thing. In other words, if you had it up that high, now 5 meters is pretty high, how much work would it do in its fall? And that's how much potential energy it lost during its fall. So it's the same type of thing. What's the M? 5.00 kilograms times, what's the G? 9.8. What units? Meters per second squared. And what's the height? 5.00 meters. Okay? And again, the units are going to come out fine, because work and energy, same units. Potential energy, it doesn't matter, same units. I'm going to need help with this multiplication as well.
It's 245.
245 What? Joules, or kilogram meter per second squared, kilogram meter squared per second squared, or Newton meter or joules. Now, here's where they get a little weird. Because this is only two significant digits there, they round this to 250 joules. I think that's being a little nitpicky, especially since they gave your other two N3 units, and a lot of physics books will use 9.80 as the acceleration due to gravity. So I would live with 245 as well, but 250 is what the book gave. Any questions about that? All right. Now, before we get to kinetic energy, the concepts applied there, work and power. If you've read that, hopefully you have. You have just been reading what we are basically going to do in lab today. One big difference is we're going to use U.S. customary units, not SI units. So, but other than that, what they've described here is pretty much what you're going to be doing. Okay. Any questions? Potential energy. Then let's move on to kinetic energy. Potential energy was the energy associated with what? Position. Whereas kinetic energy is the energy associated with motion. Okay. Now with position relative to, say, the gravitational field. So mg is going to be in there. If it's relative to a spring, you're going to have the spring constant and the amount of stretch of the spring. Okay? But if you got motion, what is motion always associated with? If something's in motion, what quantity does it always have? Always. If it's in motion, it always has a mass. Okay, everything has a mass. So yeah, it does have a mass. A velocity. Doesn't necessarily have an acceleration. That could be zero. But if it's in motion, it's got a velocity. So this is the energy associated with motion, and think of that as an energy associated with speed or velocity. Okay? Now this results from work or change in potential. Okay? And we've had some of these illustrations before. But if I do work on a tennis ball, I give it kinetic energy, right? Work on a golf ball, a football, a basketball. If I push, pull, whatever on it, hit it, whatever, I can do that. Or it can be a change of potential energy. If I hold the book up here and release, what's this motion right up here? Nothing, zero. But once I release it, then its motion starts picking up speed, so it starts gaining kinetic energy, of course, until it hits the floor. And then it stops and has no kinetic energy again. So kinetic energy can result from work being done, hitting something, pushing on something, something like that. It can also be from a change of potential energy. Now, they don't give the formula yet. Maybe they'll give it here. There it is. So you see kinetic energy is 1/2 mass, as Patrick said was there, but also velocity squared, speed squared. Now, what this representation is what happens, remember if you double the height of an object, you're going to double its potential energy, right? But what happens if you double the speed? What happens then? You increase the kinetic energy by 4 times because you're squaring that speed. And 2 squared is 4. If you triple the speed, how much have you increased kinetic energy? 9 times. 3 times 3 is 9. Okay. So, wow, kinetic energy goes up much faster with speed than potential energy does with displacement. Okay? That's a linear relationship there, quadratic relationship here. Now this has some pretty practical applications. In fact, driving home this evening is going to have some very practical applications. It did driving in this morning, okay? If you double your speed, what do you do to your stopping distance? Quadruple your stopping distance because of this. The stopping distance depends on your braking potential, and that's how much. That is a linear thing here. This is a quadratic here. So that's why you do not tailgate. Because what happens when the roads are wet? The friction is less, you're going to slide further. So spread it out, folks, or slow down, okay? Or maybe a combination of the two. Okay, you cannot expect to stop in as short a distance when you're going at 70 miles per hour as it was when you were going at 50 or 35 or any other. 35 to 70, quadrupling your stopping distance. Okay, so important practical applications of kinetic energy. Okay, and that's why when there is a wreck on one of those speedways, it does a lot of damage and could cause a lot of loss of life or limb. Okay. Wow. That's all they had on kinetic energy. Well, that's not quite all they had. They have at least 2 examples here. So let's do these 2 examples for kinetic energy. One thing we didn't do, let's go back to this. Let's figure out our units here. 1/2 is just a number, a dimensionless quantity. It has no units. What's the unit for mass? Kilogram, okay. What's the unit for velocity? Meters per second. But if you square it, that becomes meters squared per second squared. And what in the world is a kilogram meter squared per second squared? A joule, exactly. So kinetic energy, same unit as work, same unit as potential energy. Energy, work, all forms of the same thing. So the units are joules. Now, how about in the U.S. customary? We don't usually use mass, do we? Okay? So it's going to be rather bizarre using this formula. Most of the time they're going to give it to you in SI unit. But what is the unit for energy in the U.S. customary? It starts with, I can't hold it up there forever, folks. Foot. Every Monday morning I stop on the weight, which is in U.S. customary? Pounds. Foot pounds. Foot pounds. Okay. That's the unit for work. That's the unit for energy. That's the unit for kinetic potential energy. In the U.S. customary is foot pounds. Okay. Hard to see how you get out of this equation here, though. But don't worry about that. So, let's go back and do example 3.7. A 7.00 kilogram bowling ball. 7.00 kilogram. What in the world could that be a measure of? Mass. Perfect. Is moving, in a bowling lane with a velocity of v is equal to 5.00 meters per second. What is the kinetic energy of the ball? What is the kinetic energy of the ball? What was our handy dandy formula? 1/2. Second? M. V squared. Okay. Oh, and by the way, remember, I said that most of the time, when your primary variable is squared, you're going to have a 2 in the denominator. And here we do. Okay. I pointed that out before. Acceleration was that way. 1/2 AT squared. Same thing here. Kinetic energy 1/2 mv squared. Okay, let's plug and chug. 1/2 we can put as 1/2, or you could write as 0.5 times, what's the mass? What's the mass? 7.00 kilograms. And what's the velocity? 5. Ooh, why didn't everything erase there? Okay. 5.00, what units? Meters per second. But what are we going to do to that? Square it. All right. All right. Now, remember your please excuse my dear Aunt Sally? Okay, we do the exponent first. So we can do half of 7, which is 3.5. We could do that. 3.50. Now I put 0.5. You could 1/2 is 0.5 to as many zeros as you want to put out there. It doesn't matter. So I only put 1, but you could put 3 or 4 or 8 or 10 or whatever. 3.5 kilograms. Half of 7 kilograms is that. And what is 5 squared? 25. And that technically would be 0.0, but you don't have to put that. But you don't just square the number, you also square the units as well. What would that be? Meter squared per second squared. Okay, and what would that give you? Someone with a calculator, help me out here. A little louder? 87.5 what units? Joules. Excellent. That's your kinetic energy of that bowling ball. And how they do? Oh, they got it. Now, why can we use 3 digits there? Earlier we were rounding to 2. Because this has 3, that has 3. There's no G in here. G, we don't need one. So, and remember, this 0.5 can be as many zeros as you want. So that's exactly 0.5, 0.0000000. 1/2 is 0.5 with as many zeros as you need. Okay, so that was example 3.7. Any questions on that? Now, example 3.8. I can relate to this one, except I'm not sure I was ever a 100-kilogram football player. Yeah, I was. No, I wasn't. That's pretty heavy. I've never been that as a football player anyway. 100-kilogram football player. What in the world is that a measure of? That's the mass of the football player. Is moving with a velocity of 6 meters per second, 6.0 meters per second. Tackles a poor old stationary quarterback. Stationary, meaning he was not moving at the moment. How much work was done on the quarterback? Okay. Now remember we said work. Okay, in fact, let's go back one slide. Kinetic energy can change into potential energy, but potential energy also, if we went back one more slide or two or something here, where is it? Work and energy related, blah, 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 blah. Yeah, work is a process of changing energy levels. So the relationship between work and energy, you can have change of energy, whether it's potential or mechanical, producing work. So what we're dealing with here is this quarterback is doing some work. I mean, this football player, I'd say at that mass and that speed, let's call him a linebacker. this linebacker is going to be doing some pretty significant work on this quarterback. How much work is he going to do? It's whatever his change of kinetic energy is. Okay, and if after the hit he stopped, which he probably will, how much work has he done? So how much kinetic energy did he have here? So we're going to say KE initial is equal to, what's the formula? 1/2 mv squared, and this will be 1/2. And what's your mass? 100.0 kilograms. And what's your velocity? 6.0 meters per second, but you're going to square that. Okay? Well, half of 100 is 50.0 kilograms. And what's 6 squared? 36 meters squared per second squared. You square the units as well. And what does this give you? Is this about right?
1,800.
1,800. What unit? Joules of energy. He's expending on that quarterback. So that means that quarterback absorbs 1,800 joules of hurt. Okay. Now, if you wanted to use, it's pretty windy out there, isn't it? Wanted to use a smaller number but a bigger unit, what would that be? Smaller number but a bigger unit.
Oh, 1.8.
1.8 kilojoules. Okay, because kilo means 1,000, so that comma is replaced by the decimal and make that a kilojoule. Okay. Now, do we have enough significant digits here? We weren't sure here, but do we have enough here? Yes. We had 4 up there, but only 2 here, so we're stuck with 2. 1.8 is exactly right. Don't put another 0 on it. Okay. What they get, they left it as 1,800 joules. Okay. Or 1.8 kilojoules. Any questions on that? Okay. Now we move to 3.3, which is energy flow. Now we've been talking about this to some extent, except we hadn't used this term flow here. And that's an interesting term, and there's sort of a reason that I'm picking out to be an interesting term, because originally the scientists, you might say, who were studying this, they didn't know what energy was. Okay? So they sort of assumed that it was they gave this name, ethereal substance that a material would have, and so therefore if it was a substance, it could flow. We know it's not a substance, but we still use the term flow. So energy can do work against inertia. Have you ever done that? That linebacker did work against that quarterback, didn't he? The quarterback was at rest for a moment, okay? And once he got hit, he probably was moving a little bit too, if nothing else, into the ground or somewhere like that. Work against gravity. Yes, we can do work against gravity. Energy can do work against gravity. Work against friction. I'll push on this desk. Oh, that took a bit of effort. Why? Because there's friction between the feet and the floor. You could probably hear that. Okay, I could hear it. Work against shape. Have I defined work against shape with the volleyball for you before? Okay, yeah, I did work against the shape of the volleyball, if I remember correctly. I do, okay. And work against any combinations of these above or below or wherever. Yes, energy can do work in all of those areas. Let's look at a few. Here's a guy pushing on a car. The car has inertia because of its mass, and the guy pushing on it, he's a lot lighter than the car is, but yet he can still exert a force and do work on the car. Especially since it's a Volkswagen. Okay, that's a little bit of one of the lighter cars, but of course if you get it rocking, that of course is sympathetic motion or resonant motion, and you can actually get it moving if you're wise about it. But he's doing work against inertia. Okay, here the guy is doing work against inertia, but he's also doing it against gravity. The car, there wasn't any gravity. He wasn't pushing it up a hill. He wasn't lifting the car. He was just pushing it that way, so he's only doing work against his inertia. This guy's working against the inertia of the box, but also against gravity, which is always pulling down on the box. Okay? Here the gal is pushing it thing. She's doing work against inertia for one. No gravity involved because she's not pushing up or down. But the cabinet has friction with the floor. So she's having to work against friction. There was an example of that. And then work against shape. That could be springs, volleyballs, or things like that. You work against shape. Now, do most cars still have coil springs? Okay. Second?
A bunch of your trucks still run full springs, but not a lot of your cars run full springs.
Not a lot of what?
Not all. Cars don't run full springs a lot no more, but trucks do when you're running in there on a coil over. Coil over, they run a strut with a coil around.
Okay, well that's still a coil, basically. Okay, but in the heavy-duty trucks have what they call leaf spring, right? Yeah. Okay. So you can have different kinds of spring, but it's all working against the shape of the spring. Okay. Now, that leads to subtopic under this is energy forms. Okay. Now, the working energy was basically this stuff here, work against all these things. That was the first subtopic. Now we're doing energy forms. It seems like we've hit this about 3 or 4 different ways here. But let's talk about this. There's an important one. Not in today's lab, but in Tuesday's lab, we will be using this concept. The concept of mechanical energy. Mechanical energy is defined as the sum of kinetic energy plus potential energy. Mechanical energy is the sum of kinetic plus potential. Okay? So there's one energy, actually 3 energy forms. Kinetic is one form, potential is one form, mechanical is yet another form. Actually, this potential could be spring potential, it could be elastic potential, it could be gravitational potential, it could be any number of potential energies. So the mechanical energy is the sum of kinetic and potential, so you have another form. Electrical energy. That's energy that charges have and currents, as either the currents are moving charges or charges have attraction or repulsion from other charges. That's electrical energy. Chemical energy. The energy involved in chemical reaction. That's a pretty lame definition there. But what they mean by that, I think in my first class, I described what happens when solid sodium interacts with water. You remember that? Say again? Yeah, it's really an explosion. Really, it gives off an enormous amount of heat. That's because that's the energy involved in that chemical reaction. The wetting of sodium produces an enormous amount of heat. Okay? The combustion of gasoline or kerosene or any kind of ene produces a lot of heat. That's the energy involved with chemical reactions. That's why we call it chemical potential energy. Because the little green leaves out there are taking carbon dioxide from the air, more water, plenty of water from the soil, and as long as they're little green leaves, they're producing sugars, and it takes energy to bind those together. Then when we eat the sugars, we get warm, we have energy to move, all that. There's energy involved in chemical reactions. The bonding between the electrons and things of the different chemicals that adjust to different energy levels. That's why some actions are endothermic, like the making of the sugars, exothermic, the burning of the sugars. Okay, sugar, an apple for lunch with sugars in it, burning that now, I hope. Okay. Radiant energy, that is a form of electromagnetic energy. Electromagnetic energy is a form of radiant energy. Visible light is just one tiny part of that spectrum. You have everything from gamma rays, which is electromagnetic radiation, radiant energy, X-rays, lots of high-powered rays there, ultraviolet rays. Then you have this narrow little visible light spectrum, and then you have infrared, radio waves, all sorts of rays down there. Visible light's just a small part. That's what the little green leaves are using, the visible light. Nuclear energy. That's the energy involved with the nucleus of an atom. And remember, back when we were talking about it, we said those were strong. They call them weak forces. Even those weak forces are awfully strong. A lot of energy involved with that. When you're breaking up or combining a nuclei together, boy, you have a lot of energy release. A very exothermic reaction there. Okay? So the energy involving the nucleus and nuclear reactions, which are enormously large. That's what's going on in the sun right now. Been going on for about 5 billion years and probably will last another 5 billion years. At that point, it will pretty much have used all of its hydrogen and we're toast. We're done for. I may not be around. Okay. Energy conversions. Okay. This is the next subtopic here. Now, the book does a lot better job of doing a lot more things with this. As I say, usually at the end of the chapter, nothing replaces reading the chapters, so please read the chapters. Let's just see a little bit of what we've got here. This figure here shows mechanical energy, the energy of motion. What you have a propeller back there under the water that's pushing the water back, pushing the boat forward. That's good old Newton's which law? Third law, exactly. Action, reaction. The propeller pushes back on the water. That's why it turns up like that. That pushes the boat forward. That's Newton's third law. That's mechanical energy is a combination of kinetic energy, which certainly the boat has, and perhaps some potential energy of the fuel and stuff like that in there. Good old wood represents, what are they going to use that for, you reckon? Heat, exactly. Just like the energy from the sun, radiant energy, the light energy from the sun, is being absorbed by those little green leaves. They're making simple sugars. Later the plant will combine those to make complex carbohydrates. One of those complex carbohydrates is cellulose. Very complex carbohydrate. And when you burn wood, you release that energy, basically, that came from the sun that you had earlier. Okay? Now, I don't know if you can tell what this is. Anyone ever been out to Birmingport? No?
Yep.
Yeah, what do you see out there? Great big mounds of coal. That's what they do at Birmingport. They load the coal onto barges and send it down. What is that? What river is that? Warrior? Whatever river it is. Ultimately, it gets to the Gulf of Mexico and they send it to South America or somewhere. Because most of the coal that we produce is too dirty for us to burn, so we ship it to someone else because they live on a different planet and pollute the air that they breathe, that we all breathe. Okay, never mind. But that's coal. That chemical energy of the pile of coal might provide fuel for a power plant for 100 days. Okay, I don't know where they came up with those numbers. What's going on here? Top of page 73. Solar panels. They take that light from the sun and directly convert it into electrical energy. So there's another energy conversion. Here, you would take the coal is light that was absorbed by plants thousands, if not millennia of years ago, and over time and pressure and heat and stuff, it's changed that to coal, and then we take the coal and burn it, and that heats up water to superheated steam. The steam goes through a turbine, turns the turbine, produces electricity. The solar panels replace all that. They take the light from the sun directly. Now, there is chemical reaction in that, and that convert that into electrical energy. There are some chemical reactions there, but this is very direct. This was over a long, long period of time, light from the sun into electrical energy. Then, when they were talking about the spectrum, and I mentioned some of these words, very high energy, very high frequency, short wavelength gamma rays, incredibly deadly rays. Okay, you do not want to be exposed to gamma rays. Okay, do you remember the Russians were involved with the killing of a couple spies that defected in Britain, I believe it was, and what's that?
One was their daughter, right?
Yeah, exactly. And what they did, they slipped them a little bit of a radioactive substance in their food, and that was one slow, painful way to die. Because that gamma radiation released from that radioactive material just started killing structure. Killing flesh in the stomach and the intestines and stuff. Dead. It took a few days and stuff, but it was, I'm sure, miserable. Don't want to mess around with gamma radiation. X-rays, we think of good things, don't we? Except think about those technicians. Have you ever had an X-ray done? Those technicians stay in the room with you?
I had one done today.
Say again?
So I had one done today.
You did? Okay. Did the technician stay in the room? No, he got behind some dark leaded glass, and that's when they turned on the thing. You were the only one in that room. That technician's wearing some type of badge somewhere on his body, his or her body, and they're reporting how much radiation they're picking up. They get too much in a month, they're off. They can't do any more until they get the levels down. Okay. Then you hit ultraviolet radiation. Is that good stuff? No, it's not. Oh, but it gives us suntans, doesn't it? Is that good? No, that's destroying skin tissue. And that's where skin cancers come from. Ultraviolet radiation. Also cataracts. So I've had both of mine removed. Okay? And now I have artificial lenses in there. Finally, we hit the visible spectrum, and look how narrow that is. Just a tiny little thing. It goes from violet light to red light. If you do it the other way, red, orange, yellow, green, blue, indigo, and violet. Now, indigo is in there just to make Roy G. Biv. It is a color, but you can't distinguish it. Okay. And then you get below that is infrared radiation. What is that generally? Heat. That'll be chapter 4. Okay. Today, I doubt it. Unless the sun would come back out bright like it did just a couple of minutes ago for a very short period of time. But if you left your car closed up, which I bet you did with it raining this morning, right? But left it closed up and you had a fairly bright sun, even though it may have only been 40 degrees, it's warmer than that, but 40 degrees, but bright sun, when you get in your car, what does it feel like? Toast, okay? It's really nice and warm. Why? Because that visible light coming from the sun in this spectrum, when it passes through the glass, it loses a little bit of energy, lengthens its wavelength, drops its frequency, and becomes infrared radiation. Then that infrared radiation doesn't have enough energy to go back out through the glass. So therefore, the car traps the heat. And that's why it feels warm in there. And that's why in the summertime, what do they warn people about leaving in vehicles closed up?
Children.
Children or
Animals.
animals, exactly. They can die, and they have died because of infrared radiation. In the summertime especially, it's already hot, and that beam, that sun coming down, beating on that, it's going to get very, very hot. Below that in frequency and energy is microwave radiation. Cook your food with that. FM television, they really don't have, FM TV is next. FM and TV, that's in the megahertz range. Then you get down here to AM broadcast, that's in the kilohertz range. And then you get longer radio waves down here, okay? Some of those may include, maybe somewhere in here is Citizens Band and shortwave and ham and that kind of stuff is in there. Higher energy up here, higher frequency, shorter wavelength, longer wavelength, lower frequency. Okay, so that's done. Let's move on to energy conversion. That's what this slide is. Any form of energy can be converted into another form. Sort of. Okay, I don't want to just say any, always, any of those kinds of words, because there are certain forms of energy that are really hard to do anything with. And this is mostly low-level heat. You rub your hands together, you can feel them getting warmer. How can you use that heat to do anything else? There's not much you can do. The heat due to friction is usually just wasted energy. Usually hard to convert it into any other form. However, there are a few techniques and things that people are coming up with, which I think are very, very innovative. Say, if you're walking along, your clothes are moving, you're moving and stuff like this, and maybe producing a certain amount of heat, you're burning calories and stuff like this. Some nano devices that can weave into your clothes to convert some of that low-level heat into electrical energy, and you can actually charge your cell phones just by walking. Now that's a few things that are coming up with. Hopefully one of these days we'll get those perfected, but maybe we can use more of that low-level heat, okay? But they say here any form of energy can be converted into another form. Energy flows, as they used that word before, from one form to another in natural processes, okay? Usually if it's a natural process, it is somewhat reversible. And this is where Tuesday's lab will come into play. This one we're not going bowling Tuesday, that's a different. Okay, we mentioned a bowling ball earlier, but we were only dealing with it when it was rolling on the surface. Now we're going to look at how it got to rolling on the surface. Number one, what did the guy do first? He lifted it, okay? What does lifting it do? Okay, anyone ever mess around with a bowling ball? They're not light, okay? They're fairly massive, fairly heavy. So in lifting it, what's he doing? Giving it potential energy, increasing its potential energy, okay? We're going to count this as the zero reference level because that's as low as that bowling ball is going to go. So he's given it a significant amount of potential energy, mgh. The higher h he has here, as much mass as it has, that's giving it quite a bit of energy. Now, does he just drop it from there? I sometimes do, but no, okay. He also pushes it, giving it more. What kind of energy now? Well, kinetic energy, because it's now up here, it was at rest. Zero kinetic energy. All it had was potential energy here. So he's going to do two things. He's going to swing it down with his arm, so it's going to pick up kinetic energy as it loses that potential energy, but also he's pushing on it, giving it more kinetic energy, and now all it has is it's rolling down a fairly level bowling lane. Those should be pretty flat, right? I think they are. Then no more change of gravitational potential energy, so it's all kinetic energy here until it hits the gutter. No, this guy better than me, okay? It hits the pins. What does it do to them? Sends them flying in all sorts of directions, giving them kinetic energy as well. Some of them may get lifted up with a little bit of potential energy, but that's what he's doing. He's doing work on those pins, giving kinetic energy to the pins, okay? Actually creating a certain amount of heat. Also creating a certain amount of sound, which is a form of energy. When those hit, you hear it, okay? So that's more work being done, okay? This is the one I thought was going to come next. This is what we're going to do in Tuesday's lab. We're going to be swinging a pendulum, okay? And what we're going to do, we're going to lift it up a certain height, giving it what kind of energy? Potential energy, gravitational potential energy. Well, it's going to be at rest, so what kind of energy will it not have? Kinetic energy. Until you release it, and then it's going to start losing potential as it falls, gaining kinetic as it falls. When it reaches the very bottom, it's going to be maximum kinetic, because at that point, no more potential energy. Because that's at the zero reference level. It's the first thing you can measure, okay? And then, but it keeps going and starts climbing, increasing potential and decreasing kinetic until it comes to stop. And then swings back down, back and forth. That's what a pendulum does. Constantly changing potential to kinetic and kinetic to potential energy. But guess what energy remains constant? What's the sum of potential and kinetic? Uh-oh, that was 2 slides ago, wasn't it? That's too long. Huh? Mechanical energy, perfect. Mechanical energy stays the same. Okay? But kinetic is always changing, potential is always changing, but mechanical stays the same. When it's at its max, it's all potential, zero kinetic. When it's down here, it's all kinetic, zero potential. When it's halfway up here at 1/2 H, half of its potential energy, half of its kinetic energy. 3/4 and 25. 25 and 3/4, okay? It's back and forth. All right. Here is the, I like to call this mechanical energy of the pendulum. It's fixed. It's the sum of kinetic and potential. That's what we'll be doing in Tuesday's lab. Okay? Can't wait, can you? Okay. All right. Let me make sure I'm not skipping anything. All right. I really am not too sure why this figure's in here. It's showing the blades of a steam turbine. And you may not have realized there were that many stages in a single turbine. But the steam comes in and hits here. High energy steam. I don't know which end it's coming. Let's just say it's coming this way. It hits here and turns it this way. And it goes through all these stages. Obviously, this is in a narrow and then wider thing. And every time it pushes more against there, so the whole thing turns. So it's pretty incredible. I don't know why it's there, but I guess it's just showing the heat energy from the steam has become kinetic energy of the turning wheel, and ultimately that becomes electrical energy once you've gone through a generator. Okay. Now, let's see if they have, no. They do not have a figure on the slide like 317, but that's basically almost the same as these levels of the pendulum, okay? 10 meter height of release, 5 meter halfway down, 0 meter at the ground level. They do a couple of conversion of new formulas for you. So let's do that one. Let's find some slide to work on right here. Okay? Now, at the top up here, I'm going to go back and show this. Up here is all potential energy. And what is the potential energy up there? What's the formula for potential energy? Oh, how soon we forgot. Second, potential energy, gravitational potential energy. mgh. That was the whole sum of the energy at the top. Now at the bottom, that same energy is now all kinetic. And what's the formula for kinetic energy? 1/2 mv squared. And guess what? If we wanted to solve this, usually for final velocity, one thing we would do is multiply both sides of the equation by 2. That wipes out the 1/2. And then we would divide both sides by m. And looky there. The mass doesn't matter. It could be a bowling ball, it could be a tennis ball, it could be a golf ball, it could be whatever that's going up and down. The mass doesn't matter. Okay? Now we've gotten rid of everything on this side except v, so we have v squared is equal to 2gh. What if we want to know what v is? What do we do? How do we undo a square? Help me somebody. Take a square root, the square root of 2gh. So that would be the final velocity at the bottom when your initial height was h. The g's are constant, the mass has disappeared, so all you have is a variation between the velocity and the height. Height at the beginning is related to the velocity at the end, by that formula. Okay? That's your equation 3.5 in your text. So, with that in mind, let me clear my screen here. Let's do, example 3.9. Okay? By the way, y'all help me keep up. Yeah, we got plenty of time, about 45 minutes. Okay? What's that? Oh, okay. A 1 kilogram book. What is that a measure of? That's your mass of the book. Falls from a height of 1 meter. They told you that's the height of 1.0 meter. What is the velocity just as it hits the floor? You want v final, right before it hits the floor. How are we going to determine that? Second? There's a couple of ways, you pick one. Second?
The velocity right before it hits the floor.
Yeah.
We use the formula we just made.
And what was that?
The square root of
V final is equal to square root of 2gh. Now, if you remember how we did that, that's fine. If you don't, you can go back and reproduce it. Okay? So let's plug and chug. Square root of 2, I can do the 2 part. What's your g? G, what's g? Huh? 9.8. What units? Meters per second squared. Times, what's your h? 1.0 meter. Where's the mass? It's not in the picture at all. Not at all, okay? So, what do we do here? I can almost do that in my head. That's the square root of 19.6. But what units do we have? Meter squared per second squared. Okay? Those don't sound like velocity units, do they? But what do we have to do yet? Take a square root. And the square root of 19.6 is something greater than 4, less than 5, 4 point something another. But when you take the square root of the number, you also take the square root of the units, which would be meters per second, which is a great unit for a final velocity. Someone with a calculator tell me what square root of 19.6 is. It's 4 point something. Second? 9.4? Or 4.4? 4.4 meters per second. Notice in the book they got something wrong, didn't they? Did you notice that? Or at least in my book they got it wrong. What did they get wrong? They have meters second, meter times second. That's not. It's meters per second. So, yeah, make that correction there. That's a oops, boo-boo, you know. All right. Now, the second question here is what is the kinetic energy of the 1 kilogram book just before it hits the floor after that 1 meter, 1.0 meter fall?
So we take the V we just found and plug it into the.
Say that again.
Do we take the V we just found and put it in the kinetic energy?
That's exactly what they did. And what do you get? KE equal, what's that formula? What's the okay.
Oh, it's 1/2 mass times velocity squared.
Okay, which would be, I'm just going to put 0.5 times 1.0 kilogram. There, we did use that. Times 4.4, I lost it there. 4.4 meters per second squared. Now, what's wrong with this picture? Okay, you're using a rounded quantity because you had to round off to get that 4.4 to do the next calculation. So what does this give you? It should be 19.6. Half of 19.6 would be
9.7.
okay. If you use their number, but if you use 4.4 squared was 19.6, right? And if you use that, half of 19.6, 0.5 times that would be 9.8 joules. So 9.7 if you use this one, 9.8 if you went all the way back and just undid that. What happened there, when you went here to here, you rounded off. Then when you went here to there, it didn't come up as large a number as you did. So actually, what I would have done was take the actual gravitational potential energy at the beginning, which was mgh, and if you had done that, 1 kilogram times this times that, and that would have given you 9.8 joules, not 9.7. So their round-off efforts there actually came out with a less correct answer than if you'd gone back to the original. But, you know, if you're that close, you're going to get credit for it. So don't sweat it. But I just wanted to point out to you, it's a little bit dumb because it should be exactly what the original potential energy was, which was mgh, which was 9.8 times 1 times 1, okay? So it's 9.8 joules. So sometimes they're little round-offs. What you do, you propagate your errors in. That's the term for it. Okay. Now we're ready for the next slide, which is energy conservation. Okay? Couple of things about it. Now, if you remember our core concept at the very beginning of the chapter, we said something like that, this. The total energy of a system is constant, is always the same. You cannot create energy. You cannot destroy energy. You can change its forms like crazy, but you cannot. Energy is never created nor destroyed. The form just changes. Okay? Energy can be converted from one form to another. How many slides have you seen that on now? At least 2. But the total energy remains constant. It's sometimes hard to keep up with that total energy, but it does remain constant. An example of this is free fall. If you have an object up here, what kind of energy does it have? Potential, because it's not moving, so it has 0 kinetic. Once you release it, though, it starts falling. Slowly at first, rapidly as it goes on down, losing potential energy, gaining kinetic energy. So right before it hits, it reaches that maximum velocity. Energy transfer mechanisms work. You can do work. I did work on it to get it up this high, right? So I used that to change its energy level, and then I released it, and it started coming back. Okay? Other things you can do is heat. Okay? That's what's happening in a turbine. The steam turbine we were seeing earlier, it's the heat of the that's absorbed into the steam is used, that energy from that is used to turn the turbine blades, slowly uses that heat up, ultimately somewhere on the other end it condenses back to water. Okay? And guess what? You'll never use all that energy you put into it, because the energy that drops it back to being water, it's hard to retrieve that energy again. Okay. So, here's the formula we just did. It's there under energy conservation, but it was in the book under energy conversion. Okay? Here's that formula we just did. The potential energy lost at the top is equal to the kinetic energy gained at the bottom. This was mgh. This was 1/2 mv squared. Solve for the v squared final, and what you get, because at the final, that's when this goes to 0. So all the energy is this. That's why it's at the bottom. So that's your square root of 2gh, which Patrick was referring to earlier. Okay. Now, here's that figure. They've got the slide figures aren't quite matching up with the book. I thought it was in here somewhere. Here's the one that was back on page 74. Somewhere way up there, 10 meters high. 10 meters would be approximately a little more than a 3-story building. So, that part of the building down there that has 3 floors, if you're on the roof, you're about 10 meters above the ground, approximately. Okay? So you're up there, and that's where you're going to release the ball, it looks like. Okay? Now they don't tell us, we could back up and find out if mgh and the 10 was your h, that means your mg must have been 9.8, so your m must have been 1. So you have a 1 kilogram mass up there. Now 1 kilogram is maybe a little bit less than this book. That's pretty close to a kilogram. Your books would be less than a kilogram, okay? Maybe 2 books would be about a kilogram, okay? So 1 kilogram mass, 10 meters up, G is 9.8, so that would be 9.8 joules. Height, that's what it is at the top. There's no velocity because you're holding it, so no kinetic energy because velocity is 0. Now you drop it, and about halfway down, about 1.5 floors down, when it goes by that window on the 2nd floor, there you're at 5 meters down. You have lost half of the potential energy, but that's been gained here in your kinetic energy. And you can use this formula here to figure out when it's at h, square root of 2gh. Someone plug that in. Square root of 2 times 9.8 times 5. Take a square root of it. See if they did it right. Square root of 2 times 9.8 times 5. Well, 2 times 5 is 10, so that's square root of 98. See what you get. Okay, they rounded to 9.9 meters per second. Perfect. Okay. I just said square root of 98, square root of 100 would be 10. So this is just under 10, 9.9. Okay. But then when it reaches the bottom at 0 meters, now it's just right before it hit, all the potential energy is gone because the H is 0 down here. All of this is now kinetic energy, so that's your 98 that you had from the beginning. So what's your velocity then? Well, you can use the same formula and do 2 times g times 10. So this would be 2 times, because it's 1 kilogram mass, it's 2 times 98, so it would be 196. Square root of 196 would be 14. There it is, 14 meters per second. So were you expecting the speed to be half the speed, halfway down? No, it's considerably more than half, okay? So half what it would be at the bottom. Because that varies with the square, not linearly. All right, any questions on that? All right. Now, again, they don't have these slides quite in the right order. Ooh, they don't have these slides in here at all. Okay. Let's back up one here. I kind of like this slide. It's really busy slide. Now, I'm sure you can't see it well from where you're sitting. But just about all the energy here on the Earth, just about all, not all, but just about all, came from the sun. And at the sun, you have nuclear reaction going on continuously. Like I said, it's been going on for the last 5 billion years or so, and it's scheduled to go for about another 5 billion years or so. Okay? So this is nuclear energy of the sun, but it could be from other places too. And you can actually, sort of a new term here, laser-induced fusion, you can make it go one way, but gamma radiation coming from that is the energy coming from that. So you can reverse this, but that's a pretty involved process. That creates radiant energy, that spectrum we just saw. Gamma radiation, X radiation, ultraviolet radiation, light radiation, infrared radiation, radio, I mean, just all those different kinds of things. That's your radiant energy. Now that is captured by the little green leaves out here. Photosynthesis is stored in chemical energy. Or that radiant energy is heat energy, and that powers a heat engine, okay, for mechanical energy. Or that radiant energy could be absorbed by a solar cell and directly become electrical energy. And you could put all other kinds of energies on here. They just did a fairly simple one here. Now, you could burn that chemicals that you made with your photosynthesis and remake heat energy with its radiant energy. You could take that chemical energy and a type of chemical energy, put it in a battery, and you can make electrical energy from that. Two potential differences, okay? Two metals with different potentials. Or you could take that chemical energy and burn create heat and turn a turbine into mechanical energy, okay? Let's see, we hit all the ones leaving chemical. Okay, and you can go all the way around here, back and forth, just about every way. Every form of energy can be changed to other forms of energy. Okay, they don't show all the connections, but they show a lot of them. Okay, so that's a pretty good diagram for illustrating what we're talking about with energy conversion. Okay, now that and energy conservation as well. That then leads to this slide. And again, have we seen this before? Do you think this may be important? They mentioned it at least 3 or 4 times now. The flow of energy, energy is never created nor destroyed. Okay? Energy can be converted from one form to another, but the total energy remains constant. So here's another picture of that same type of thing. The nuclear energy of the sun going out through all of space. Our tiny little planet out here, the third rock from the sun, is absorbing just a small portion of that, but actually our atmosphere is blocking most of it, only allowing through a very narrow window of visible light. Okay? The infrared radiation, the ultraviolet radiation, most of it's getting blocked, not all. Just about all the gamma radiation, just about all the X-rays, that's getting blocked, not entering our atmosphere, thank goodness, or we'd be dead. We wouldn't be able to sustain life. But the light energy that does come through, the radiant energy, does hit the little green leaves out there. They form simple sugars, maybe more complex carbohydrates, possibly some fats, like nut trees, those are almost totally fat. But we consume from the trees, from the plants, from the grain, from the other things, or from the animals that eat the leaves, from the other things, and then we consume their meat, and we get that into our bodies. We have chemical reactions there that enable us to power our bicycles, to do whatever it is we're going to do. Read books, study, okay? But at some point, everything converts back to heat, and even this process is heat, everything's heat, and that radiant energy is back into the atmosphere. Okay? All a big cycle. Now, is any of it getting back to the sun to recreate more nuclear energy? No. The sun's going to burn out in about 5 billion years, they think. Okay? And then planet Earth will be toast. Okay? But not my body. I don't worry about that much at all. I don't think mankind is going to make it 5 billion years, frankly, just between you and me. We haven't made it very far this time, and we're going downhill fast. Okay. That shouldn't be too pessimistic, should it? Let's look at some of the energy sources today. Okay, this is 3.4 in your text. And this is pretty interesting to look at. This slide here was from a text probably 5 to 6 years ago, and it may have been older data. But wait a minute. There's a myths, mistakes, and misunderstandings here. Should you leave your computer on or turn it off when you're not using it? It says there is a myth that leaving your computer on all the time uses less energy and makes it last longer. Okay? If that was ever true, it's really not anymore. Same thing was said about fluorescent lights. Because there was sort of a surge at the very beginning, early fluorescent lights, they said, yes, it takes so much energy to turn them on, it's better to leave them on, especially rather than turn them off and on, off and on, off and on. Because every time you turn them on, there's another surge, you're using more energy than leaving them on. They've got most of that corrected now. Most of the time, if you're not using something, turn it off, okay? That's my theory anyway. The book seems to be supporting that, strangely. All right. Then there's this diagram in figure 3.20 on page 76. And you'll see there is a little difference in what we see on the older slide and what we see on the more current slide. So this is pretty interesting to look at. Energy sources today, back when the older slide was done, 40% of the energy we were using was from petroleum. That was some type of liquid that you got out of the ground, okay? 40%. Nowadays, they say that's dropped to 36. And again, this slide is probably a little bit old, so we may even be less than that now. Number 2 before was coal at 21%. Okay? Nowadays, dropped to 18%. And, if I'm not mistaken, is even dropping further. I heard on the news sometime in the last week that one of the big coal companies was entering bankruptcy because people just aren't using as much coal as they used to. It's dirtier, it's not as efficient, and I also heard this comment made. I don't really mean to get too political, but I think I am, okay? A previous president warned that coal was on its way out and offered lots of training for people who worked in the coal industry so they could retool for new jobs. A more current president came along and said, no, we're not going to lose any coal jobs. We're going to conserve these coal jobs. And now the plants are closing. He made promises, offered nothing. The other one said, look, this is happening. Train for it, get ready for it. They're losing jobs and have no training. So sorry about that, folks, but that's the reality. Okay? Oh, I said that was number 2 before. No, actually it was number 3 because natural gas was 23%. But look at natural gas now, 27%. Now, what is largely responsible for that increase, you think? It's a word that's been in the news now for probably 5 years or so, maybe longer. Second? It's the process. Second?
Global warming, fossil fuels.
Okay, well, that's all this is contributing to that, but the process I'm thinking of is called fracking. Have y'all ever heard of that? It's a process by which they're able to pump stuff into the ground and get more natural gas out. Okay? And that's been used very successfully. And natural gas is much cleaner, much cleaner than coal, quite a bit cleaner than petroleum. That's why that's going up and the others are going down. Another factor in there, most of our petroleum, we've spent a lot of our resources. Texas oil fields, Oklahoma oil fields, Mississippi, there are various places in the country that had oil fields. We're used up most of that. And most of what's left is hard to get and pretty dirty, okay? We've used the sweet prime stuff. So we've been importing for decades. Well, we're trying to lead ourselves off the importing petroleum, so we're doing our own fracking. We are now almost energy neutral as far as what we use and what we produce. We still import a lot, but we also export a bit too. Like the coal from Alabama is too dirty for us to use, so we send it to South America. Okay. Not good. Okay? Now, that was number 1, 2, and 3 in the old slide. Number 4 in the old slide was nuclear at 8%. Look at what it is now. Nuclear at 8%. Oh, this isn't quite now, but close to it. Okay? Why has that remained not increased? Does the location 3 Mile Island ring a bell? What happened in 3 Mile Island?
We talked about it in class about 2 weeks ago.
Oh, this class. Yeah.
No, we talked
Oh,
about it.
another class. Okay. I thought I couldn't remember that we did it here, but I talked about it a lot. In the previous class, I think we mentioned it, didn't we? Not sure. Okay. Okay. Now, 3 Mile Island was as close as the U.S. has ever come to a nuclear meltdown. We didn't quite have one, but boy, we were close. Or some people may have claimed it was one, but it was fairly well controlled. Up to that point, we were building nuclear power plants pretty rapidly, okay? But something happened just a few years before 3 Mile Island. Anyone ever heard of Chernobyl? What was that? Yes, that's in Ukraine, which was then part of the Soviet Union. They had been building nuclear power plants really, really rapidly, but they weren't putting as many safeguards as we did. They were cutting a few corners, and they got a little sloppy. And boy, when they had a meltdown, that was a meltdown. Okay? It was serious. Deadly serious. I don't know if the figures have ever been released of how many people lost their lives when that melted down. Not just in the plant, in the communities around the plant. It released an awful lot of radiation. Very deadly radiation. I'm sure 3 Mile Island released some. There may have been some deaths that were attributed to that, but minimal compared to Chernobyl. Now, it was in Ukraine. And can anyone remember the year? It seems like it's 80 or 81, something like that.
In the 80s.
Huh?
It was in the 80s.
In the 80s something, okay? Now, about less than 5 years ago, I would say, or right around 5 years ago, there was a kid in my Math 100 and later 112 class. He had been going to Jeff State, but he was having terrible trouble getting through his math. His parents knew friends of ours, and our friend said, well, Charles teaches math at Boston State. Let him go there and take his math, okay? Here's the story of that kid. His parents, let's start with them. The father was a pastor, and the wife, worked with him a lot and things. And a group of churches from here in Birmingham had started a program to bring kids from that area in around Chernobyl to bring to the U.S. to spend the summer in the U.S. just so they could develop normal. Because this was like 20 years after the meltdown, but the area was still so contaminated that kids were not developing properly. So they had been part of that, and they brought over this coalition of churches brought over kids every summer just to give them one summer of nuclear-free growth time, and it helped. So they had made several trips back and forth, and at one of the trips they had visited an orphanage because a lot of the parents over there, when their kids were born with defects, they abandoned them. So the orphanages were left to raise the kids. And the orphanages in the Soviet Union at the time, Ukraine now, were not the very best in the world, okay? And they fell in love with this kid. He was bright, he was cheerful, he was just vivacious, but he only had one arm. He was born with a birth defect. He had, what is the lip?
Cleft palate.
Cleft palate, yeah. He had some developmental issues too, but he was a beautiful kid, a wonderful kid, just only had one arm. I think there was one finger that stuck out of his shoulder or something like that. It was just really bizarre. But anyway, they adopted him, brought him to the U.S., nurtured him. He just thrived. Had trouble learning because there's some cognitive problems there. That's why math was really hard for him. But he came, he worked hard. I recorded my lectures. His mother could listen to him, help him do the homework and stuff. They slugged through it and made it through it. I think got a C, but he worked hard for that C. But he was a good kid. He was sat right back there where Thomas is sitting. That's both classes. He was born 25 years after the explosion, after the meltdown. Nowhere really close, but in that general area, he was still affected by that. Okay? It is not something to mess with, nuclear power. That's why when 3 Mile Island happened in the U.S., after that had happened in Chernobyl, they said, stop it. No more nuclear plants. And until just a few years ago, in that time interval, 20, maybe 30 years, not a single new nuclear power reactor was activated for generation of electricity in the U.S. Now, I happen to know, because it was in my home county in Georgia, I was raised in Georgia, Plant Vogel on the Savannah River there got permission to open the first new reactor. They already had 2 running. They were opening a 3rd one. More powerful, more, everything. Technology was so much better. But the safeguards, they were putting them in like crazy. And I think if it hasn't come online yet, it's very close to it. They've already run the power lines from there to Atlanta to get it to provide the power. So there are maybe a few new ones happening. Other things also happening throughout the rest of the world. France didn't have a lot of fossil fuels, so they started really expanding their nuclear power production. Japan, poor little island nation Japan, volcanic islands. There's not much coal in volcanoes, okay? That just doesn't exist there. They were newly formed land, no coal deposits, no petroleum deposits, and they were very industrial. They were building nuclear power like crazy, which was sort of surprising, because it's the only nation on earth that has had 2 nuclear bombs dropped on it. And yet they said, nope, we're going with nuclear power because it's the only way we can power our economy without having to spend all our money by paying somebody else for fuel. Well,
that tsunami that did mess with the nuclear power.
What's that?
The tsunami that hit Japan.
Yes, that's exactly where we're going. Fukushima. At Fukushima, okay, remember I said Japan is a volcanic island, or a chain, near a fault. That's why there's volcanoes there. These people in 111, Ring of Fire, that's part of that ring. So, just off the coast of Japan is one of the faults. And that's where they built the nuclear power plant. And there was an earthquake there. The tsunami swamped the plant, even though all kinds of safeguards had been put in place, but it still swamped the plant. And it was pretty bad. It was probably as bad a meltdown as Chernobyl, except they had all these safeguards in place. But the thing is, when the tsunami hit, the power went off. The pumps couldn't pump. The water cooler, nothing worked anymore. And all the redundancy they had, nothing worked because of the force of the tsunami. Now, like I said, it was a pretty serious amount of radiation release, and someone had to go in there and deal with it. And this, to me, is one of the most incredible stories I've ever heard. Some of the old, retired nuclear power workers from Japan. Japan has a really strong honor system, and those old retired workers said, do not send in your young technicians. We remember enough of how to run the plant. Send us in. Our lives are about over anyway. Don't sacrifice the next generation to clean up this mess. Let us go and clean it up. And a whole bunch of retired engineers, technicians, and stuff like that went in to do it. Whether they died of natural causes or still alive, or their exposure to that hastened their death, they still wanted to protect the young. Incredible. My hats are off to them. They deserve some sort of reward. Hopefully they'll get it. Okay, nuclear power, just about steady. 8% several years ago, 8% when this book was done. Now, notice the next block. In your on the slide up here, we have biomass, hydro, and other geothermal and solar. You add those 3 together, you get 3 plus 4, 7%. In the new text, 9%. Biomass is renewable, hydro is renewable. We've only increased by 2%, but we're moving in the right direction with that. Definitely moving in the right direction. We need to increase that big time. Okay, so sort of disregard this. Look at the one in the book, and you'll see This is shrunk a little. This is expanded a little. This is shrunk a little. This has stayed the same. These have expanded a little. And with great promise to expand more. So let's look. Energy sources today, okay, it's not quite today, in the old past, way past. But not that many generations ago, primarily wood. That's what was burned for heating homes and lots of other sources. The early trains, wood burning to make the steam to power the trains. That then changed from wood to coal. That's about the time that Birmingham was born, and I guess Bessemer too. They discovered all this coal here. We were the magic city, or Birmingham was the magic city. It just bloomed after the Civil War. Okay, so coal, and that's what they later used for trains rather than burning wood. They burned coal, and power plants burn coal. Lots of places burn coal. I had a Toyota vehicle a few years ago. When I would take it to Jim Burke for his routine maintenance and stuff like that, the old guy who gave me a ride on the campus, it was almost always the same old guy. He was retired, but he was remembered back in the old days of Birmingham. And he said, women knew not to wash their clothes something like every other Monday morning. Why? Because that's when they blew the steam into the boilers to get all the crud off of the boilers so they could be more efficient again. And stuff just went into the air, and that stuff was not nice. If people had their clothes hanging on the line that day, they had perforated clothes when they took them in, because it would just eat right through the fabric. So women knew not to hang out the clothes on whatever days they were blowing the boilers, whatever they called them. Okay? Coal was pretty nasty. And they said that the Magic City was a pretty ugly city. And the south part of Birmingham, they call it South Highlands, because you're going up Red Mountain, and you sort of got above the haze that was down there around Sloss Furnace and everything else. That's where the first suburbs were. People were trying to get out of that mess. Now Birmingham, very clean, relatively speaking. Of course, we've lost a lot of our industry, replaced it with medical and stuff like that, which is not bad. But we're from wood to coal, from coal to petroleum. So now from petroleum to natural gas. Okay, in many ways we're moving that way still. With increasing industrialization, we went to more efficient, a little bit cleaner forms of our fuels. Okay? 89% can be traced to photosynthesis. All this petroleum, photosynthesis from millennia ago. All this coal, photosynthesis from millennia ago. All this natural gas, photosynthesis from millennia ago. Biomass from photosynthesis. Okay? That's most of it. 40, 21, that's 61, 84, and 3, 87. That comes pretty close to their 89, right there. Photosynthesis. Sun's providing all this. Photo meaning light. Synthesis meaning making, made with light. Okay? What are the uses for this energy? About a third of it is burned for heating. Okay? Heating of homes. Now, we don't do as much of that, but up north they do a lot more. 2/3 burned in engines, automotive, diesels, trains, planes, automobiles, burned in engines, and or generating electrical. 2/3 there, about a third for heating purposes. Okay? Let's look at these individually. Now, how are we doing on time? What's that? We got 5 minutes? Is that what you said? Okay, about 5 minutes. I don't know. How about let's pausing here. We'll pick up here on Tuesday. Okay? I'm doing too much talking. Yeah, I hear, yeah. Oh, I heard that. Okay. All right. Now. Let me end this. All right, sorry. Okay. We're going to 5 different stairwells. Each team is going to be 2 people. One team will have 3. Is anyone not particularly desiring to walk or run up and down a flight of stairs? Okay, you'd rather not, you be in the team of 3, you can be the recorder. Okay? And the other, and so all the teams, everybody else able to do it? So we'll be in teams of 2, and what you'll do, I'll explain it when we get there. First thing you're going to do is measure the height from floor to floor. Okay, you're only going to do 1 floor. Now, what it's wanting here, if you'll notice on the data sheet, which is the back page, okay, they want the height in feet. Okay, now these are meter sticks. 3 feet goes to 36 inches. So don't use the whole meter stick, only go to 36, and I'll show you how to estimate how many feet it is from floor to floor. Okay? So that's the first thing we're going to do. We'll determine the height of the steps. Then, each team, and I'll demonstrate this too, the flights will start here, there's a landing here, and then the top's here. The timer will be on the landing in the middle. So you can see when the person starts the walk, starts the clock. Okay? And they walk up the stairs. When they make that step on the top, stop the clock. Okay? Now, this probably is not realistic. That was 6.94 seconds. You know how to read these clocks. Hopefully, whoever's using the cell phone can do it. One of my batteries died. I had 5 stopwatches, but 1 battery died. I asked them to order more, and they haven't ordered them yet. Okay. Oh, I wanted to add some more things to the order. Still haven't ordered. Okay. So anyway, you'll do walking up the stairs. Okay. Then each person will, they say, run up the stairs. I do not want you running up as fast as you can. I want you running up as fast as you safely can. I do not want to be filling out any accident reports today. Okay? I don't want the paperwork. I don't want the headache. I don't want to have to clean up the well, never mind. Okay. So you go up as fast as you safely can. I don't want any tripping, anything else. Do it safely. Okay? So now the other thing is asking for your weight in pounds. Okay? Now, maybe some of you guys are a little sensitive about that, or maybe some of you gals are, but at least put something down. Hopefully close to reality, but it doesn't have to be exact. Okay? And then once you've done each volunteer, you're going to have 2 people per team. One's doing the stopwatch for one, then you turn around and do it for the other. Okay? So once you've got your data filled out, then come back to the classroom and we'll do the calculations. So you fill out your weight, your height, you'll figure that out first, the time it took you, each person to walk up the stairs, and the time it took to run up the stairs at a safe pace. Come back to the classroom, we'll do the calculations here. Okay? So, what I'll do now, I don't think I'll need the projector any longer. Do y'all want to take a break first before we get started, especially since you'll be running up and down stairs? Okay. Why don't you take a quick break and let's meet down at the stairs right by the restroom, right at this lower level. When you go down this half flight of stairs, let's meet at that stairwell, however long it takes you to break. So let's try to be there in less than 5 minutes if possible. Okay? Okay. Have you got your teams yet? 5 teams?
Can I team up with them too?
I'm sorry?
Can I team up with them too?
No, the 3 people are going to be with him because he can't do the run.
I'm old. I can't
Ah,
do
yeah.
Yeah.
Okay. You got a team? Who's the team? Okay, who's the team? Who's the team? Okay, one more. One more. Okay, I'll take it down there. Wait, before you go, let me give you a stopwatch. Who's got a clock you're going to use? You're going to use yours, okay? Okay, each team come get a watch. See y'all. You need a stick. Okay. Excellent. Okay. Who needs a watch? You need a watch?
I got one.
You got one. Oh, I thought I'd given you one. Okay. I'll take the other 2 down. And that's going to be about it. I'm going to take my computer as well. The trouble is my computer has a weak battery. I'm going to leave it plugged in until right before I go down there, and then I'll do it. From this floor to the floor up there. Now here's a little bit of a problem, folks, and you can't see it from where you're standing maybe a couple of you can. You see there's a ledge there, but the floor is below that. So you need to estimate where the floor is according to the concrete blocks here. Okay? So what you'll do, if someone will hold my computer, okay, let me borrow a meter stick. Only we're going to use the inch side, the feet side. So we're going to 36 inches, that's 3 feet, 6 feet. Now I would suggest come across here, assume these tile are about even, level, and then you'll do 9 feet and keep on going until somebody up there at the top estimates where the floor is here and measure to the nearest foot how many feet from the floor level to here. Now on your lab, it says measure each step and multiply by so many. That introduces so much error, you know. This is not free of error either, but at least you get a lot better guess. So that's the first thing you're going to do, estimate to the nearest foot how many feet from that floor to the floor up there. So somebody will need to be up there, the other person here until you can reach up and pass it up. Okay, that's going to be what you do first. Whose was this? Yours? Okay. Now, what you do next, I've got a clock. Now, if one of the teams need a clock, I've got 2 more stopwatches.
We'll take one.
Okay. One other team need one?
Sure.
Okay. Let me use it for right now. Okay. So,
Never mind.
let me illustrate. Now, the person with the watch is going to be up there. But let me illustrate walking the stairs. You know, this is plenty for walking. This is a nice leisurely thing that would have started up here and then stopped up here. Okay? Whoops. Clear. Clear. This is messed up. Hit the wrong button. That's why. I got it. Okay. So starting again is at 2 o'clock. Stopping's at 2 o'clock. Reset is at 3 o'clock. But be sure you record it. Now, first step is when you start it. Last step up here when you stop it. Record it, then clear it. Now, the running the stairs. Again, do it safely. Okay? This is adequate for running. Now, I have a bad knee, so I'm not going to run the whole thing, but that's adequate. Walk it very gingerly, run it at a safe pace. Any questions about that? Who wanted the other watch?
We have one.
Huh? Yeah. Another team need a watch? Okay. Who are your teams, by the way? You two? You two? You two?
Me and Diamond.
And you three? And you two. So one team doesn't have a watch, do you? Or two?
We're gonna use our phone.
Huh?
We're gonna use our
You're going
phone.
to use your phone.
They
Okay.
thought
That's
that they
fine.
needed one, but he already has one. That's what
Okay.
I'm saying.
Okay. All right. Thanks. Are there any questions about how you conduct the experiment?
So we only go to the platform right there?
No. You go from here to the top. That's why you measure to the top floor. Measure from this, you run from this floor to that floor.
So you measure the
Okay.
steps in between to get to this one?
Second?
When you get to the top, do you measure the steps in between?
No, you just time it from here to here. The steps in between are just part of the journey.
That's what
Yeah.
I'm saying.
Yeah. If you have to stop the rest, you need to go to a PE class. Okay. All right.
Are we all using?
No, okay, that's what I'm going to say. Well, how about the team with three? Is that you three? Why don't you stay here, this one. The other people come with me. Okay, y'all got a watch and a stick. Okay, good. All right. Now, I'm going to pause this for a moment. So I'll repeat some of what I just said. Okay, everybody got your weight. That's row one. The first two blanks should be the same because it's the same volunteer. Didn't lose that much weight walking up the stairs. And the second, those two should be the same. Vertical height of the stairs, all four of those should be the same. But be sure you round it to foot, whatever it is in feet. Don't put inches, miles, furlongs, or anything else. Then the third row only has a blank for the walking time, for volunteer A and for volunteer B. Then the fourth row has two other blanks for the running time for volunteer A and the running time for volunteer B. Then the work done, just like it says, force, which is weight, times distance, which was your vertical height in feet. So those answers are in foot pounds. And notice there, the work done by volunteer A, same whether you walked or ran. F times D. Force, your weight, times the vertical height. Volunteer B, those two should be identically the same because your weight's the same, vertical height's the same. And those are in foot pounds. Now, for the power generated, is everybody there or past there? Okay? That would be the work from the line just above it, divided by the time, which is the two lines above or the line just above. The time for the walking is work done divided by that time, or for the running, the work done by the time just above it. And that would be in foot pounds per second. FT-LB over S, foot pounds per second. Is everybody up to snuff on that now? How do you get the horsepower developed?
Take your power just made,
The power, the line next to the bottom line, and
you're divided by 500.
by 550. And that will give you a number in HP, horsepower, not Hewlett-Packard. Okay. Now, did anyone get more than 1 horsepower? Okay, walking?
No.
No.
Definitely not.
Okay, definitely not. Okay, you may have got more than 1 horsepower running. Depends. Okay? But does everybody see a difference there between walking and running on both power and horsepower?
A whole horsepower difference.
What's that?
I got a whole horsepower difference.
Yeah, okay, that's fine. Depends on how fast you run. Now, that's the bulk of the lab here, but that's not all the lab. Turn back to page 126. Results. Explain why there is a difference in horsepower developed in walking and running up the flight of stairs. Page 127. Now this one, the wording is a little bizarre on this. Is there some limit to the height of the flight of stairs used and the horsepower developed? And it says explain. Now to me that's a very vague question. What do you interpret that to mean?
Do you have a set number for the height?
Okay. So in other words, if you were not just using the stairs here in the A building, but you were using Brian Denny Stadium, and would you get the same horsepower after running up those flights of stairs?
You'd be in shape if you did.
What's that?
You'd be in shape if you.
Yeah, if you could. So yeah, you're probably not going to maintain the same speed going up a lot taller. So there probably would be some limit. Your endurance, anything such as that. Okay? So you probably won't maintain the same horsepower if you did 3, 4, or 5 flights as opposed to 1 flight. Now, number 3 might take a little bit of thought, but it should be reasonable. Could the horsepower developed by a slower moving student ever be greater than the horsepower developed by a faster moving student? What you think? Number 3. What's that? What would be the difference?
The difference would be the weight.
The weight of the student. If the slower moving student was significantly heavier, but not that much slower, then he could produce more horsepower. Because horsepower depends on force times the distance divided by time. Okay, very good.
Wait, what was that one? It
Okay.
was
Could the horsepower developed by a slower moving student ever be greater than the horsepower developed by a faster moving student?
So if it was a slower moving student, way more?
It was significantly heavier, right? And not that much slower. You certainly could produce more work in just a little bit less time, or more time. Still be greater horsepower. Okay? Now, number 4. I may have already done this. Describe an experiment that you could do to measure horsepower you could develop for a long period of time rather than a short burst up a stairwell.
A mile. You could run a mile.
Treadmill.
Second?
I would say a treadmill, we could change the.
A treadmill, yeah, a treadmill that you have in an inclination, you can do for a much longer time. Excellent choice. And what was the example I just gave? Yeah, Brian Denny say it, or Jordan Hare if you're an Auburn fan, okay? Or even the old gray lady, okay? Legion Field, okay? That would work too. I've walked those stairs. If I were running them, it would be a lot more than short bursts up a stairway. Number 5, be sure you answer. However you want to answer, you can. If there's no answer, no credit. If you answer any way whatsoever, you get credit.
Mind going over number 2 again? 1 and 2.
I'm sorry?
I didn't get 1 and 2.
1 and 2?
Yes.
Okay. On the results,
Yes.
explain why is there a difference in the horsepower developed in walking and running up the flight of stairs? What's the difference? What made a difference there?
Speed.
Okay. Oh, that's related to it.
the time.
The time. It took longer to walk the stairs than it did to run the stairs. That's what horsepower depends on, work divided by time. So if the time was different, the work was the same. You did the same work whether you walked the stairs or ran the stairs. It's the time it took. That's what made the difference in horsepower. Okay?
2.
And number 2, is there some, that's a really bizarre question. Is there some limit to the height of the flight of stairs used and the horsepower developed? I don't know how to answer that, but I would probably say probably so, because at some point you just can't run any further or faster, and you reach the limit of your endurance. So there has to be a limit somewhere there. I don't know if that's what they were asking. It's such a vague question, but that certainly doesn't matter. Because like I said, you can develop, like Jay said, he went more than a horsepower when he ran. You think you could do more than a horsepower up Brian Denny? I doubt it. Okay? Maybe you could, but that would be awfully hard to do. A real short burst, yeah, you could probably beat a horsepower or come close. But if given a long enough haul, you reach a limit of your endurance, your ability. Now, number 4, and many other classes where we haven't talked this through, people just did on their own, they would say, well, run a mile. And that sounds pretty reasonable, but you know what? If you don't have elevation change, if you're on a flat track running a mile, that's not the same thing. You need elevation change. So run a mile if it's a very hilly mile, okay? Like any course you would find in Birmingham, okay? Like they do for the Mercedes marathon, those things, that's up and down hills. So that would be okay. Stadia would be fine. Your treadmill at an elevation, that would be fine. Any of those are excellent examples. Just to say run a mile, you'd have to say up and down hills, because you'd have to include that in your. You have to have a vertical change for this to work well.
We can go turn them in to you.
What's that? Yeah, when you finish the lab, you can certainly turn it in. If you need some more time to prepare your formula and equation sheet, you can certainly have that here. If you want to go and get started on the test, hang tight and I'll get with you in just a moment. Got to find the test first. Okay. Good, thank you. All right, got it.
My fingers stuck to it.
Test 2, Chapter 2 test. You ready? Okay. You can have formula and equation sheet, scratch paper, calculator. Everybody got one? Now, on this, most of them are multiple choice. Yeah, right there, it's fine. Thank you. Most of them are multiple choice. Number 7 is a calculation, and number 11 is a calculation, and number 18 is a calculation. Now, what do you remember about calculations? I'm looking both for numbers in the answers, right? But also units. Okay. deal. Thank you. You don't want to test, don't you?
Do you mind if use the
But
restroom
not
for a
the
tech-
key.
do you mind if I use the restroom for a technical
I can't
test?
hear you.
The restroom, can I use
Oh,
it?
absolutely. Yeah, yeah. Ooh, I'm recording.